in which allow the cell to change while doing the dynamics. Michele spent a lot of time also working on meta-dynamics to accelerate the molecular dynamics because we know that it takes time. And recently, he's also been working on machine learning interface potentials. So today, I think that the talk is going to be about that. Michele has been in very different institutions, IBM Zurich, ETH Zurich, at the CSCS in Switzerland, Lugano. And I see now that he is at the Istituto Italiano di Tecnologia. So he's doing a huge amount of work, and it's a real great pleasure to have him here. So we're looking forward to the talk. Thank you very much, Michele.
Okay, thank you for the introduction. As some of you might know, I spent many years at ICTP in Trieste, and so the institution there in Kigali is dear to my heart. So much so that I'm doing things that I really hate to do, giving a Zoom talk, but because you don't have a perception of the audience, and it's all very cold, you can. But anyhow, here we are. Let's hope in the future we can meet, and then I can also enjoy the enthusiasm of young African students. They're always marvelous. Okay, so let's go. And okay, what's happening? Yeah, now it's going to play up. Okay, now it obeys in a only special way. My talk is not really about methodologies, but about what methodologies can do, and especially in a field which is really important, chemistry. Chemistry in complicated situations. So let me put this way. So it has been mentioned earlier that we developed the Parrinello, and one of the application of the method, the natural application, is chemistry, because you have the possibility of breaking and forming bonds. And so I became part also of the chemical community and went to the talks. And I was always surprised of how rigid the approach was for many, not all, but in many theoretical scientists. So this is a typical diagram, which is shown also in textbook. It's a very important diagram. You have two states, A and B. This could be reactants and product, it could be liquid and solid. So we represent in this way typical transition between two states which are separated by a free energy barrier. And to me, it seems in my naive times at the time was that what most of the quantum chemists would do is to calculate with great accuracy A, great accuracy B, find the transition state, and that was it. I mean, that also other people were not completely happy with this approach, which is certainly highly successful. And here I quote from the Nobel Prize speech of Gerhard Hertel. I was studying catalytic process, for instance. I will come back later. Catalytic process which have to do with the production of ammonia. And he recognized already almost 30 years ago that I mean this approach was at its own limit, and to really understand catalytic process, you have to resort. He mentioned Monte Carlo technique, but if you change here and you put molecular dynamics, it still holds. I think it will not, it is just a different method of doing statistical sampling. Okay. And of course, we were with Roberto here. When we discovered or developed the ab initio method, we were very excited by the possibility of using ab initio molecular dynamics, in which the interatomic forces are calculated, say, from density functional theory, and so capable of describing the formation and the breaking of bonds, that we could really address this kind of problems. And we were able to address lots of problems, but not as many as we were hoping at the time, and because there were many hurdles to be transformed this method into a generic tool to describe complex chemical processes. And I mean, really, ab initio molecular dynamics is not cheap, and so the simulation which can be done with ab initio method, we are limited in complexity, the accuracy, the time scale, and well, that's not a problem with ab initio, but in general, when you do simulation, at the end of the day, you want to get an understanding of what you have done. Okay, so let me move to sketch the step that we and others have taken to take the ab initio MD and make it into an even more powerful method. Okay, and bottom line is that ab initio molecular dynamics is expensive, and we need a new set of tools to address more complex problems. One step which is important, and it's relatively recent, is the fact that it's expensive. Can we maintain the accuracy of DFT and still have a potential which is cheap to use? And this is possible if we use neural network, because neural network can express functions of many variables in an explicit form, and that's what we did now it's 15 years ago with Beller, and it was Beller and Parrinello. There is an error here. There are no other authors in this publication, and at the time, using neural network was a bit premature. The theory and the practice of training neural network was not that developed, but very recently, much progress has been done. There are many codes which one can use. There are libraries, PyTorch or something else, which don't need to program complicated neural networks. There you can develop them yourself. So it has this approach has really boomed, and there are now millions of ways of building neural network-based potential. The bottom line of this approach, there's the same accuracy as ab initio MD, but they are much cheaper. So we don't need to compromise on the accuracy, and we can perform at the same time of calculation that DFT allows. Of course, you have to train, you have to decide which which configuration you train your neural network on, but at the end, it's much cheaper than running a full ab initio calculation, and many applications have been made and will be, many more will be possible in the future. Okay. But that's not all, so that's a big step, it's very important, but still there are many things to do. So if we want to study a complicated system, we also want to understand how things go, what is the physics, and so on and so forth. This cannot be done on the basis of the potential energy surface, which is very high dimensional, and it's very complicated and rugged. This is an artist's impression of how this a potential energy surface might look like. Of course, we can represent only two-dimensional things, so we imagine this in a space of hundreds of thousands of dimensions. So to make sense of this and to focus on one or more of the events that we want to study, we introduce the CV, the collective variable, and the concept of free energy. So collective variable and free energy are associated, and the result of this is that we go from a very complicated potential energy surface into a smooth, low-dimensional free energy surface. The free energy surface, of course, introduces entropy in the description of the system. So the free energy is composed of enthalpy, energy, and entropy, which is very important. Okay. Okay. In the past, I just alluded a few things that have happened and have made the determination of collective variable easier. Huh? So collective variables were determined heuristically and formally. I mean, if you are mathematically or theoretically inclined, they can be defined as the slow mode of the evolution operator. So you can imagine you have a Boltzmann distribution of your system, you evolve in time, and the collective variable will be the variables that represent the modes which are the slowest. I'll give you an example of this, and which I think is instructive. Suppose you have a landscape like this, and you ask yourself, if you try to move from left to right, what are the slow modes? And of course, the slowest mode will have to be associated to the highest value, because that's what it takes. That's what slows down the propagation of your system, is the presence of this mountain. If you go from A to B, you have to overcome this mountain. And this is how one collective variable looks like. They all look like this. So we have a value roughly constant in one basin and the value roughly constant in the other, and it goes from one basin to the other in a sigmoidal fashion. Then the second mode will be associated to the second slowest variable, and that's it. And then we have the third mode, which is associated to the third variable. Okay, this mode, now you can use machine learning to determine these modes. I will not go into how you do it, but just know that the difficulty of finding collective variable is still there, it's much simpler to determine collective variable, and in many cases can be done almost automatically. Okay, so So that's these are two things that we wanted to say preliminary. Then we move to, I think, some of these things I talked about last time. I gave one such talk, and I apologize for those who already know these things. But one issue that is even what we discuss here, collective variable, is a way of analyzing the system. But I feel there is an important, you have to get the data. And to get the data, you cannot rely on standard molecular dynamics, because it's even you can cover, I can follow the evolution of the system for so much, say 1 millisecond if you're a rich person. But many chemical and other physical problems, they take place on a time scale much longer. And so if you simply have the best potential and you run your simulation, at the end of the day, you will not you will not get the result, because if you have a liquid to solid transition, you start with the liquid and you remain with the liquid. So you have to come out, simulate the system of going, say, from the liquid to the solid. And the way we do is in pictorial way, so that we start with the original Hamiltonian, with original problem, which is complicated, can resemble to exploring, say, the landscape of Switzerland, and making it into a more gentle landscape, like the one here in Tuscany. It's a typical, I'm Italian, so you will forgive me for this, making this patriotic example. So you, rather than moving into through the mountain, which is difficult, we want to move and explore the more gentle landscape of Tuscany. But that's not enough, because you have to be able to go back, and then something, my program is playing up, it's not going back. Never mind. Okay, so let me see whether it works in this way. Okay. Okay, now it goes back. Okay, so you want to be able to go from the original problem to a problem which is simpler to solve, and then go back to the original problem. That's basically what methods, which are called the non-sampling, do. In fact, most non-sampling methods, these acceleration methods, they are based on the same concept. So you start with a distribution which is very, very sharp, like this, and you transform into a target distribution which is gentler and simpler to solve. And there are various examples, for those that know, various examples of different biasing or acceleration methods that are based on the same concept, that you transform your original distribution into an easier to sample target one. And there are very many different ways. I mean, for many years we have used metadynamics, but what we do now is something a bit more fancy, which is called OPES. The details are complicated. Again, you introduce the target function, but in metadynamics, you try to reconstruct V, but in OPES, you try to reconstruct the probability distribution. And here comes machine learning to our rescue, because in data analysis books, there are millions of methods to represent a probability distribution, and we can use this method to make the method more powerful and faster converging. Okay, so this, I think we can skip it. Some of the things that happens when you run this method. And so we move to some demonstration. And that's the famous example. When you do this enhanced sampling, this is a small molecule, alanine and dipeptide. I forgot an E at the end. And it has a conformational flexibility, and this, especially this two angle, phi and psi can change, and the free energy landscape will look like that. There is one minimum here, which corresponds to the low free energy conformations and the high free energy conformation, and there is a barrier between the two. Now, we can compare how metadynamics and this new OPES method perform, and we can see it here. On the right, it's already done, while metadynamics still struggles. And one characteristic of OPES that, it's going it all over again, you get the generic feature very fast. And then what you do is just, you just optimize the detail, determine the detail. So these are just one which will come back, and one of the this idea of looking at an unsampling method as method of mapping one distribution into the other allows us to perform what I call kind of a miracle. So suppose that you want to determine the phase diagram of some substance. What you have to do is check position, pressure, and temperature, do a calculation. Then you move, then you move, then you move. So you have a grid of n points, and you have n simulation to perform. Now with this multi-thermal, multivariate, you just do one simulation, and you get all the data in this little square. So you determine you want to do an interval of pressure, an interval of temperature. You sit in the middle, and with this method, you can get information on all this range of pressure and temperature. Okay. We have applied this approach in many areas, and I think what I will confine myself to doing today, I will not talk about biomolecules. I focus on application to chemistry and materials, and you will see that the kind of chemistry I'm talking about is very linked to material properties. And so I know that I presume at least the audience is mostly interested in material science, so we have a chemical process in which material science plays an important role. Okay. And the first example I want to discuss is the called Haber-Bosch process. I alluded to this before. That's a catalytic process for the production of ammonia. Ammonia is a very important chemical because it's at the basis of the production of fertilizers, and it has avoided famine in the world because it can produce fertilizer artificially. And all over the world, there are millions of factories that produce ammonia, but this is a very intensive, energy-intensive process, and so significant fraction of the world energy is spent into producing ammonia. And so that's interesting per se. The other interest in the ammonia production is that people think that it's a way of storing hydrogen, because ammonia NH3 is rich in hydrogen, and so if we have a process by which we take ammonia and we decompose into nitrogen and hydrogen molecules, then we can say build an ammonia production factory in a place rich of sun, like Africa, and so I use clean energy to produce ammonia. Then ammonia would put into pipe ducts, and then transport all over the world. And then when you need it, you decompose it, and you have part of your energy back in the form of hydrogen. Okay. And so let's imagine, this is a process which is 100 years old, but still not well understood. And there is, in my group, a big effort to try using this technique to try and understand the process, with the idea that once you understand what happens, you can improve and maybe reduce the energy consumption and things of this nature. Okay, so that's a cartoon in which we kind of imagine how things work. We have a nitrogen molecule, comes down on the surface of iron and is split. Hydrogen does the same. On the surface, the two, the N and H recombine to give ammonia, which then flies away. Okay. Now the iron structure plays an important role. Different phases have different catalytic properties, which is already interesting. And among the surfaces which are important for the process, there's the 111, the 100, and the 100. Okay, so these are very old experimental data which show that that indeed the surface which is most catalytically active is the 111. Of course, this, once the method became accessible, also theoretical calculation have been done. In particular, Norskop group has been a major player. And he has studied the absorption of the first step of a reaction, which we also, so the N2 molecule that comes down on the surface and then splits. And what he did, he identified different absorption sites. So the nitrogen flies down the surface, can sit on top. This is position which is called gamma. And then it can go to another position where it's on top of a second layer iron atoms, or can lie down. This position is called alpha. Instead of standing up, stands down. And then if you, it's not very visible here, but in another picture you will see that there are little cavities here. So you have a molecule in the top layer, there's a second layer, and down there is a third layer atom that is exposed. And the nitrogen molecule, when it lands there, is here, has still a small barrier, but then you can go into the beta, into the dissociation. So it's a precursor to dissociation, being able to get into contact with this atom, which is called C7, because it has 7 carbon neighbor. And why this is a catalytic site? Because that's it is a site which is kind of rich of electrons, and to break the NN bond, which is very strong, you have to pump electrons into this bond. And we'll see this concept playing on further. Okay, so this calculation, now here you see better the cavity. That's a better picture. So this is the one-on-one surface. The lighter atoms are the top layer. Then they have the second layer and the third layer, and this is a small catalytic C7 site. Okay, this is what happens at 0 temperature, and I think it's a regime in which theory and experiment agree with one another. But the difficulty is that this process takes place at 700 Kelvin, at high pressure. So are we sure that what goes on at 0 temperature is the same that happens at 700 Kelvin? That's the big question, and experimentalists have difficulties in operating at this temperature, and so there are not data here, and so far also the theory has been absent in this range of temperature. So we try to cover this hole and try to understand whether we can learn from 0 Kelvin what happens at 700 Kelvin, or if there are new things going on. Okay, so the first bit, so we do all this hocus pocus, so we get the potential, and we look at the, I have to look at my at the time. I look at what happens first to the iron surface. Okay, so this is, we try to define what is a surface, and we look at the surface roughness, the density of this catalytic site, if there is diffusion, and so on and so forth. And so that's what we do. So this is how a surface at 700 degrees looks like. It's far from perfect. There is a lot of activity. The roughness is increased. I mean, it's very hard to find the C7 things. There is a diffusion going on. And you see, I tagged one atom yellow to see where it goes, but all atoms do the same. There is nothing special about the yellow atom. It just goes wherever the thermodynamic condition. So the first layers of this of iron, they are far from being flat or even resembling what happens at T1. In retrospect, this is not surprising because of the main feature of this thing is this cavity. So it's a not very dense surface. And so if you increase the temperature, this is the most prone to be destroyed. Okay, so there are other things. The coordination number in the real, in the T equals 0 situation These are the coordination number of the atom at the surface, but when we move, there's an infinite possibility of coordination. And this you can see also here. We color the things according to the atom, according to their coordination number. And you can see also in the direction perpendicular to the surface, there is a lot of action. From the fourth and so on, the lattice is more stable. It's just a phenomenon confined to the first few layers. Okay, so now we have a hot surface. We want to send a nitrogen molecule on the surface and have it to this sort, just to see what. So there are two phases. One is the absorption, and then there is the dissociation. This is a recapitulation, so different sides, the gamma, vertical on the second layer, horizontal deep down. Okay, and that's this studies suggest that the simulation proceeds as discussed here. Now we run the simulation, but before we need to understand what goes on, and if things move all over the place, it's very difficult to define what is a gamma, alpha prime site, but we realized it's a very, very important factor. That if we look at the electronic properties of the system, we can distinguish whether a system is in the gamma, in the alpha, or in the alpha prime position. And we can do that by looking at how much charge is transferred from the iron into this molecule. So you see here, that's with the color, we indicated that a lot of charge has been transferred here. Let's saw here there is more charge, and it's even more charge being here. So if we look at what we are called the charges, we can identify unambiguously the absorption site without having to rely on geometrical considerations. So this is a movie. The periodic boundary condition break the molecule in unlikely place. Okay. I think we don't. Now, if you want to calculate the Bader charges, you have to do a ab initio calculation. Okay. And what Bader does, it takes the electronic density, divides in pieces which belong to the different atoms, and measures how much charge there is relative to the reference charge, the nominal charges. Now, you don't want to do this calculation at every step, because as we said, that's too expensive. So what we did was to train a neural network that can predict the atomic charge. So we have a number of DFT calculations, calculated the charges, but then if you take an arbitrary configuration, we can ask the neural network to predict the charges. And that worked very well. And so what we're going to do here, now we have all this data, the simulation, we have seen one such a simulation, and we want to have the free energy, and we use this here as collective variable, the N2 partial charges, which I think is a very nice thing to do. And if you look at the free energy surface, this is the distance from the surface. So this state here, where Z can go forth and back a lot, This is the non-absorbed molecule. You see the charge is low. Then we have the gamma, and we can see the gamma and alpha, they are not very distinct. Then we have the alpha. If we increase the charge, we increase the thing. Okay. Oh, that's what it is. That's a gamma. That's the alpha. And you see, this is really buried inside the surface, and that's why it's a catalytic site. And it's very similar to what they said, but I mean, at this temperature, it's not possible to distinguish well between the gamma and the delta position. Okay. Now we can compare. It's instructive to do the calculation in which we take the atom frozen. It's a frozen lattice, but the molecule can bounce forth and back on the surface, and we find this energy profile. Now, instead, we do with the mobile the real thing, and we see that there is this great difference. In particular, the alpha prime site, which would be a minimum, now becomes a poor shoulder. This is the consequences, and this is totally then different from T equals 0 profile, because T equals 0 is doesn't have all this effect of the lattice. Okay. Now we go to the last thing, and that's where I will stop and leave time. So this will be the grand finale. So we look at the reaction, and we compare three different simulations. One with a static surface, and the other two with a dynamical surface. Okay. So let's do the movie of the static surface. Okay, so this is the alpha guy. Then it goes directly into, the delta, sorry, I'm mixing up. And then it goes into the alpha prime, deep down in the cavity, and it breaks down. Okay. Now, let's do the same thing. See, we have a nitrogen close to what looks like a C7 site. Okay. I forgot to click the table, and there is time to break the bond. Now let's do the mobile charge. You see, things come and go. That's what happens. At a certain point, the C7 site is no longer there, and before the molecule breaks, it has gone. And then we go. There is a beta. Okay, now. So then that's it. Then we go to a more lucky things. Well, eventually this guy manages to get to find the moment, the fleeting moment where the thing is there, and it breaks. Okay, and so that's it. So what is the consequence of all these things? The consequence is, of course, the reaction rate at this temperature, which we can calculate, is not what is predicted by the Arrhenius law. It's much lower. It's much lower because of all these different phenomena that I try to discuss with you. So the effective barrier is much larger, and therefore the catalytic activity of the real T equals 700 Kelvin is reduced. I think I've used my time. I don't think I have time to go to discuss this, so I will move quickly to the acknowledgements. That's the wonderful group that I had over the years. I mean, these are not the latest. So, for instance, Ali Hassanali is not here, is already left. And we don't have very recent ones because of COVID, but hopefully we can start again having having this group parties. Many people have put money into it and helped that. I forgot the ETH here, but we have a collaboration with different entities in Germany and with different chemical companies. And in particular, I want to acknowledge my collaboration with Professor Schlöger here, who's a real chemist, not and who has kind of guided us, sort of guided our hand in writing this piece of research. And I like to end up with this motto, which is, I think how I see science that should go on. That there is, it's from a Spanish poet of Between the Wars, the European World Wars, and it means that there is no path and you have to find your path as you go. And that's the end, and thank you for your attention. If you I'm ready to answer your questions.
Okay. Burakoze. Okay, Burakoze. Yeah, Michele, thank you very much. Please, can you tell us a little bit about your method for your simulation of gallium? I know you skipped it, but if you just highlight.
Okay. So let's go because of that. So let's we go. Well, I'll do it quickly. So gallium is a very intriguing system because it has a very peculiar bonding and a complicated phase diagram with different crystal structure being possible. And it has a very low melting temperature. If you hold it in your hands, it will melt. And it has an anomaly on density like in the case of water. As I said, these are not the polymorph. You see, one has even 7 neighbors, which is an oddity, beta and gamma. And the construction of the potential, the neural network is a bit elaborated, and we had to go to self-consistent, parallel self-consistent cycles. So we have an initial guess, we collect the configuration, we do DFT calculation, we train a neural network, we do it, we run again, until this loop is arrived at self-consistent, and we use this isothermal isopressure thing. We find a very good agreement between theory and experiment. Also the phase diagram, we get essentially right. The scale is very large. And so it looks like terrible, but actually the error it makes, considering the complexity of the system, they're small. And we can look also at the kinetic of the solidification, because there are various anomalies. So can be at temperature, can be overcooled a lot, undercooled until to extremely low temperature. If you Undercool, I think it first goes into the, depending on the undercooling, it goes either into one phase or in the other. And I think we have an argument why that happens. Okay, so that's more or less it.
Yeah, thank you very much. So, sorry, let me ask two questions related to this. So when you did the neural network training, you use all the structures that I think you'll find, or which structures did you use?
No, we can't. That would be too. So I'll give you an example. One, but then you adapt the procedure to. So one of the first real physical application of the neural network, we studied the crystallization of silicon. Okay. And which is always challenging because silicon is a semiconductor, but if you melt, it becomes a metal, and metals so there is a big change in bonding between one and the other. And so what we did, we started with the potential, in this case, feeling the Weber potential, and we did the simulation. And we did a simulation, however, of crystallization with this potential. So we can collect the configuration that belong to the liquid state, configuration that belong to the solid state, and also configurations that are intermediate between the two. So we collect, I don't know, a few thousand, I forgot the exact number, let's say 1,000 or 10,000 this configuration. We try to choose them in a way that they are statistically uncorrelated. We use calculate the energies, the FT for this selected structure, and we the network on those data.
There's a question from the audience, Michele. So you mentioned in your introduction biomolecules. Have you examples that you can mention about that?
It's a bit complicated, but I just tell you that there is a lot of noise. I mean, could people who don't speak shut their microphones? Because I really can't, I can hardly hear. Okay. So we looked at the problem of ligand protein binding. And where you have a ligand that goes into the enzymatic center or the binding site of the enzyme, we were able to illuminate the role of water. Usually, I mean, this process was studied only looking at the distance and the contact between the ligand and the atoms in the cavity. But we realized that the water itself has an important role, and that not only the number of water in the cavity, but also the structure that water has in the cavity play a role into the cavity, both the binding energy and the kinetic of the process. So I qualify this as a complex chemistry because of this very factor that they're not as simple as they look. Like in the case of iron, which is more complex. To start with, even T equals 0 is a complicated thing, but I will stop share so that I can look.
Thank you, Michele.
Okay.
Any other question? Yes, it's one here. Yeah.
I have other questions.
Thank you for the nice talk. My question is on identifying active sites on heterogeneous catalysts.
Yes.
Okay, so one of the ways that I've seen in papers is experimentalists give a suggestion as to this is a possible active site, and then those that do computations to confirm. Is there a way of doing it in the reverse, like the computation scientists identify the active site and then the experimentalists now confirm? Is there, have we been successful in doing that in the field of computations?
I think that is possible. That is possible, and actually it's a good project. It's a good idea. I don't know whether people have done it, but certainly it is would be a worthwhile. I think what has happened I presumably is that theoretician had an idea, and then the experimentalist then on the basis of calculation, and then the experimentalist verified. But in my talk, there was one extra bit relative to it. I will say that there are situations in which that are complicated, in which the very notion of catalytic site is questionable. So if you look at this almost liquid surface, where you have a molecule floating on top of it, it's more, and then once the molecule of the surface arranged at the right time, in the right moment, then it can dissociate and makes this, which is classified as heterogeneous catalysis, more like a homogeneous, so in 2 dimensions, in the sense that it's like a reaction in a solvent, in a reactive solvent kind of thing. So I would say it's a hybrid between heterogeneous and homogeneous catalysis. So there is not a defined static catalytic site. I got an answer.
Yes.
The question from Bala. Huh?
Yeah.
Hi,
There's
Bala.
a question. Yeah, there's a question in the chat.
Yeah. Is there a definite research effort in replacing natural? Yes, indeed. I don't know. What I heard is to use like the sun, alternative energies. As far as that's where there is so the green ammonia is called. Then they call the blue ammonia when they use methane.
Sorry, I have a question. So in your simulation with nitrogen on ion, so all the ion atoms have the same spin state, right?
Yes. No. We fix the magnetization of the system. So it's a ferromagnetic piece of iron, which I think is what it is. But you're right. I mean, the atoms in the surface could have a different. That we don't know how to. I mean, at least at equals 0, if one compare the rates, where there are data, the rates that are obtained by the theoretician and compared to the experimentalist, this seems like a good a good way of treating the problem. Oh,
Okay.
a reasonable way, let me put this way.
Okay. Thank you.
Welcome.
I think there's no more questions in the audience. The chat either. So we thank you very much, Michele, and especially given that you said that you hated doing this kind of online talks. So we really appreciated that here at Kigali.
I was not fishing for compliments. Okay.
Thank you very much. Yeah, thank you.
Okay, okay, so read.
So thank you, everybody. And then we meet again tomorrow, starting at 9 a.m.